Okay, so we're looking specifically at exam technique today, and I'm interested to know where you think you're losing the most marks in organic chemistry, particularly with exam technique. Because I mean, okay, it could be that you just don't know stuff, and that's where you're losing most marks. Hopefully, if you came to yesterday's class and you're thinking about how to improve your revision, that will no longer be the problem. So forgetting the whole, I don't know the answer, where else are you losing marks, do you think? Or which are the most difficult parts that you find? While you're thinking about that, let's have a look at what, oh yeah, silly mistakes, definitely. There's always a reason for silly mistakes though. And one of the things is about knowing what to look for in a question. So I like that. Silly mistakes is a big one. What we're going to look at today is very briefly using your data booklet. I'll explain when we get to it. We're going to look at command words, which is really important, and identifying key command words is a way to avoid silly mistakes and other sort of knowing what they're looking for. Synthesis and reaction pathways, so they look at some ways to try to not let these types of questions get out of hand and maybe like stress us out, because that's another reason that we make stupid mistakes, is if we get overwhelmed by the size of some of these organic questions. We're going to look at some tips for analysis, so your infrared, mass spec, NMR, like where to start and like the best order to approach those types of questions. And hopefully we'll get a little bit of time just to look at some unfamiliar mechanisms, what we do when our mechanisms, like we're not seen them before or they don't look familiar as well. Okay, so that's a lot to get through. Let's challenge accepted. Okay, so data booklet, what do I mean by that? So silly mistakes can include mind blanks. And when you are in an exam and you're stressed because it's a chemistry exam, it's going to be hard. One of the things that I really notice is functional group blanks, completely gone. You've forgotten the name of everything. So this is where your data booklet, depending on your exam board, can be super helpful. So if you're doing Edexcel, you are on the best winner because you have the most information in your data booklet. If you're doing OCR, you're probably like second place. You've got quite a bit of information. If you're doing AQA, I'm sorry they don't put quite as much in, but they do put a few clues. And the clues that I'm talking about are these lists. These are lists of functional group names. Sometimes all you need is the word. So sometimes you just can't remember it. It's on the tip of your tongue. All you need is to look at this list and be, oh, ketones, that's what I was trying to remember. Like I couldn't for the life of me remember what that thing was. If you're really lucky, if you have a look at like this infrared table, not only does it just give you a list, it gives you a list of the bonds that are in there as well. So one of the things it does is, for example, tells you that all of these have C double bond O's. If you were trying to remember which one was amine and which one was amide, you can see that amide comes up with a C double bond O, but amine isn't here. So you can remember little things like that as well. Just give me a moment because I've lost my Zoom. So I'm just going to bring it back. There we go, just in case anyone is. Oh, no, I'm having a crash, but I'll keep going anyway. Okay, so that's where our data book can be really, really helpful, depending on your exam board, of course. Okay, let's get rid of that and completely, hopefully bring everything back. Perfect. Now we're going to look at command words, and command words is so important that I have kind of put it into various different like ideas and things that we need to do. So command words. reagents and conditions. What do we need to look for in the kind of things that it's asking for? So if it says reagents, we're talking about things that go in the balanced equation. So things that, actually react with the molecule in question. So an alkene and HBr would be a reagent, or bromine, for example. Okay, that's hopefully obvious. Conditions can have way more information. So conditions could include temperature, could include a catalyst. So temperature for organic is normally not a specific thing. It's just whether we need to heat it or not. And if we're going to heat it, we know probably by now, we're normally going to heat it under reflux. That's just a rule. It's not a rule all the time. So you need to watch out for whether you need to heat it under distillation because you want to make something else, or if you want to heat it below a particular temperature. That's very common for benzene reactions. Or if you have a specific temperature, it's usually because it's a gas reaction. Okay, so like having to know a few reactions, like 150 degrees, something like that. Catalysts have to be specific, but actually, like a lot of the time, we might just have acid as a catalyst. Benzene, we're going to have aluminium chloride pretty much every benzene reaction. And then gas reactions have solid metal catalysts almost entirely. So if you're stuck and you can't remember and you're trying to add hydrogen, pick a transition metal, platinum or nickel. They usually work for gas reactions. Solvents are more important than we think. So they can make a difference. They can give you a different product. But the main thing to sort of revise and check out for is there are lots of things that react with water. And that is why we have a lot of reactions that say things like ethanol solvent or dry ether solvent. So if you see dry solvent, it's because something would react with water, because water is a very reactive liquid for a lot of organic reactions. And pressure is very rarely needed for organic chemistry. It's only needed if you've got a gas reactant like ammonia, for example, or if you've got two gases like an alkene and hydrogen. Most of the time we're heating under reflux. Reflux is open. We don't have it under pressure. It would explode. Okay, so reagents and conditions, very common. Look out for specific command words such as name of a reagent or formula of a reagent. So talking about silly mistakes, underline things such as name or formula. Maybe do a little arrow down to the box just to remind you, because you really don't want to lose that mark. If it tells you to give a name and you write Cr2O72 minus or something like that for an oxidizing agent. If it says identify, name or formula. If you're not sure on the name on the formula, don't write it. Just put the name down. Personally, I think formulae are probably easier to remember, but that might just be me being a chemistry teacher. The other thing to realize, and it depends on your exam board how picky they are, is that the name or the formula for a reagent should be a whole compound. So what we mean by that is sodium hydroxide, not just hydroxide, or potassium hydroxide. Most of the time, we're just going to stick a group 1 metal in there. Potassium dichromate, not just dichromate. Potassium cyanide, not just cyanide. So if a question says, what is the name of the nucleophile, or identify the nucleophile in a reaction, it's okay to say hydroxide ion, cyanide ion, or give the formula. But if it says, what is the reagent, some exam boards, particularly Edexcel, can be a bit specific and they want the name of the whole thing. Like, what would I ask my technician for in a bottle? Not just which ion I want. And also look for making sure that, of course, some of these reagents require other stuff to be present. So dichromate always needs acid to be present. Okay, So reagents and conditions are important. Look for name, formula. What about if we're asked to test? So another common thing would be how to test for particular organic functional groups. And there's a little page in your little workbook to remind you of lots of the different chemical tests that you could be asked. So we don't want to go learning all those chemical tests and then lose silly marks because we didn't quite give the information that they're after. So if you are asked for a chemical test, and this doesn't have to be organic, this could also be for, ions, testing for ions as well, inorganic stuff. You need to say exactly what you add, and you might have to add two things. So you might have to add acid as well as silver nitrate, which is not really a organic test. You might have to add something and then heat it. So you may have to add acidified dichromate and heat because the reaction won't happen at room temperature. You have to heat Benedict's reagent if you're testing for an aldehyde. So you say what you add and you say what you see. And sometimes we need to say more than one color. We need to say what it looked like before we added it as well, and just say like what the change is. If you can't remember it, just don't put that in and hope that it's not going to be in the mark scheme. But common things I'm talking about, obviously, dichromate goes orange to green, or Benedict's goes from blue to brick red precipitate. Or we could be talking about orange to colorless for bromine water. So sometimes we need a color change. And then the thing that I really notice is this is all good if you're just asked for how do I test for an alkene, how do I test for primary alcohol, how could I test for an aldehyde? But often the question is asking how can you distinguish between 2 or 3 different compounds? So you need to remember to put that comparison in. Be obvious. The aldehyde turns Tollens, you get a silver mirror. You add Tollens reagent, you get a silver mirror. The ketone, you get no change. That's all you need to say, but say the obvious. You've got time to do it. Don't lose marks on chemical tests. Okay. Don't forget also that some things are not color changes. They are as simple as just fizzing. Like if you want to test for a carboxylic acid, you can simply just add some sodium carbonate and see it fizz because it's an acid. It's not always like a specific organic test that you're doing. Sometimes you can stick some indicator in, and that's sort of enough to tell you the difference between compounds. Okay. So we've talked about chemical tests and chemical reactions. Types of reaction, I'm not going to tell you them all because you've got them all summarized, or at least you've got the first 10 of these summarized. The reason I've got 1, 2, 3, 4, 5, 6 on the left-hand side, it's not just because I ran out of room. The ones on the left-hand side of this slide are ones that you have to do mechanisms for. And you will notice that almost all of them, or at least the first 5, have 2 words or 2 parts. They have the type of reaction, which is either addition or substitution, and then they have the way that that reaction happens, the mechanism by which it takes place, which is either by free radical, electrophilic, nucleophilic. So if you've seen questions that say, give the name and type of reaction, or the type and mechanism, that is what they mean. They don't care which way around you do it. They're just looking for 2 parts, electrophilic addition or nucleophilic substitution, for example. Elimination is not on every exam board for the mechanism. It is mostly there as a type of reaction. AQA, you definitely need to know the mechanism for 2 types of elimination. Sorry about that. Oxidation and reduction are on the right-hand side because you don't need to know how they happen. You just need to know what to add to make them happen. Condensation is one that people forget a lot. And I put a little star because if you have the pleasure of doing AQA, then you may also be calling that addition, elimination, and you have to know the mechanism, which is why it's on that side. Opposite of condensation is hydrolysis. And then I've just added a couple more. There's only two types of polymerization in A-level chemistry. It's addition or it's condensation. So if you've got a question, it's about polymers and it says what type, you're only looking for those two things. Is it addition? Is it an alkene? Is it condensation? Is it an amide or an ester in the product? That's it. So just make sure that you can identify them. Use those little revision sheets to help you remember like which reagents do which. Okay, we've talked about words, but often it's not about the words. In organic chemistry, it's about drawing compounds. So it's pretty important to think about where we might go wrong in drawing organic compounds and where we can make our lives a little bit easier. So last time I chose my pen, everything went wrong, but I'll give it a go again. So displayed formulae. You need to most be careful about OH bonds and C triple bond ends. That is the most common mistake that people make when they're doing their displayed formulae. Also, sometimes we just get like CH3 groups, like you do everything correct and then you just draw CH3 because you're getting tired of writing all the bonds and then you lose your mark. And then our next bit, which is not letting me do for some reason. I don't think the pen's working very well today. So give me a moment and I'll get back to it. I won't draw on it. It was a nice idea, but it's not working. Ah, there we go. Lose it. Go. Oh dear, now I'm like one of those awful teachers in lockdown who's just like not in control of their computer at all. That's why I should have used my iPad. I know. Okay. Right, let's get it back. So, skeletal formulae. Skeletal formulae, you're only going to have to draw skeletal formulae if it actually asks you to draw a skeletal formulae. You do not have to worry about it any other time at all. So you don't have to force yourself to do a skeletal formula if you don't want to. So that's one thing I want you to be aware of, because sometimes what you'll see is like it'll give you the skeletal formula or something and you'll feel pressured to do it. And sometimes we don't like skeletal formulae. Common mistakes with skeletal formulae is really make sure you're counting your carbons, because when you add something on like a chlorine, it's very easy to chuck off a carbon by accident. So be careful on those ones. If a question just says draw the structure though, you can do what you like, so long as it's clear what the structure is. So long as it's clear which isomer you're drawing, for example, you can't get away with just drawing a molecular formula. And molecular really is like very simple and very basic. If it says draw a mechanism, again, do it how you feel comfortable. If you want to draw every single bond and do the whole thing displayed, you can, even if they've started the mechanism in a different way. So even if they started the mechanism skeletal, if you really think you're going to mess up because it's in skeletal formula, there's nothing wrong with you drawing it underneath as long as you draw the right molecule and then doing your mechanism for that. If you're like, oh, I can't cope with the cognitive demand of doing a skeletal formula and doing curly arrows at the same time, and people do make more mistakes when they're doing it from skeletal formulae because it's like 2 levels of difficulty. You don't have to. You can redraw it. You got extra paper if you need it, use it. Because if it says draw the structure, it does not mean you must draw a structural formula all in one line with like brackets around your OHs and brackets around your CH3s. Structural is like, it's not really a specific type of formula. It is just, it's not fully displayed and it's not skeletal. You can show the bonds in between carbon atoms in structural, or you could not. You could show branches coming above and below your molecule, or you could do it with the brackets. So however is easiest for you to draw a structural formula, so long as the atoms are in the right order, so long as you don't have bonds pointing between two things, like a bond sticking between an O and an H, then it's absolutely fine to just kind of keep drawing it how you want to. Okay, so I basically said you can draw organic molecules how you like, unless they say draw displayed formula or draw skeletal formula. You know there's going to be some possible differences to that. Bond angles. So another thing we might get worried about is like we might have a picture in an exam paper that shows beautiful sort of 3D drawings, lovely skeletal formulae with all the perfect angles. So does it matter what your angles look like, or can you just draw your nice 90-degree carbons everywhere? So there are 3 occasions where bond angles are going to be important and you have to pay attention to them. One is hopefully obvious. You can't draw EZ isomers unless you have something above and below your double bond. If your double bond is then a straight line with other carbons, you can't see which groups are on the same side or opposite sides if you don't have sides for them to be on. I would also say that that's a thing to do for always for alkenes if you're drawing polymers and repeat units. Again, you need to get the side groups, the bits that aren't in the double bond, out of the way so that they don't end up joining onto other carbons. Similarly, optical isomers are about arrangement in space as well. So you therefore have to show a spatial arrangement. You have to be able to draw a few things backwards to make sure that the right things are bonded in the right place. And the other one is hydrogen bonding. I'm quite surprised at how many students don't know this. So every hydrogen bond has a hydrogen, which is sandwiched between 2 other electronegative atoms. So 2 O's typically, or an O and an N, or 2 N's, something like that. That hydrogen has to be, the angle between that hydrogen and the other 2 elements around it has to be 180 degrees. So hydrogen bonding has a specific angle. It's not just a little attraction, it's an actual kind of semi-bonding kind of interaction. So it's got a specific angle. That's also important if you were, if you're doing AQA, I think you have to do quite a lot of the stuff in between different nucleotides in the middle of DNA and stuff like that, and show how they bond together. But hydrogen bonds, 180. Doesn't matter about the rest of the molecule, just making sure they have the right angle around them. Okay, so you can choose your formulae. What about if I'm writing an equation, like a balanced equation for an organic reaction? Can I just choose any way I like to represent the organic molecule? Does it matter if I do displayed or if I do structural, if I do skeletal? Obviously, if there are command words, draw it displayed or draw it skeletal, you're going to have to do what they ask you to do. If it just says write an equation, for example, addition of HBr to propene, there aren't any rules other than you have to show the sort of minimum to show that you know what the product is. So this is not good enough because you're expected to know there are 3 carbons, there's 1 double bond. You're expected to know that there's a major and minor product and that the bromine goes in the middle. There probably would be more clues in the question, like to produce 2-bromopropane, or it might say formation of the major product, so that you know the bromine has to go in the middle. So if you know that, then you have to show that you can't just lump atoms together. Again, if I was adding Br2, it's not good enough to just go C3H6Br2. We need to know that you know that 1 bromine goes on 1 carbon and the other bromine goes on the other carbon. So you're being a lot more specific about it. Similar example. This time, this question is specific starting material to bromobutane. So writing C4H7Br isn't good enough because I would assume C4H7Br was one bromobutane because you've just stuck the bromine on the end. So it might be a lot easier to do that. It's like, I know, I'm just going to swap the Br and the OH and I've done my equation. You just have to make your life a little bit harder by doing something like this. Okay, that might again be something where you're like, I'm not quite sure really whether I could do that correctly. And we've talked about silly mistakes, and silly mistakes can really be losing out on hydrogens or putting too many hydrogens in. So if you think you're going to do that, then do it kind of semi-structural, so that you're actually showing what's going on around that carbon. You're much less likely then to actually make mistakes in terms of, you know, putting the wrong number of hydrogens in, because you can see your 4 things around your carbon, and then you're just going to swap and put the OH in there. Again, you could do it fully displayed if you want to. It just might take a long time, and you might miss a bond out if you try to do it fully displayed. So doing a little combination like that is much more useful. Final example for this one. Let's say that I was going to make an ester. And again, that's not a good enough formula for an ester. So you might be cheated and go, I know, oh, I can't really remember what's going on, but I know that we lose water because it's a condensation reaction. So if I just take off water and then just put the rest of the atoms together, no, you have to show that you know what joins onto what. So at an absolute minimum, showing the C double bond O and then the O and then the C3H7, so you know how those groups joined together. Again, if you struggle with things like condensation reactions, draw it completely rather than, oh no, my days, didn't choose the right thing, pen. Draw it so that you've got the whole thing, maybe not that bit, and then draw the other bit, and then you can sit there and work out that you're going to take those out. And notice that what I've done is I've turned them round so that they are pointing to each other. And that's a helpful way of kind of working out what's going on if you draw your molecules so that the functional groups are pointing at each other, and those are the bits that you know are going to react, rather than drawing them always left to right. Okay. Finally, with writing equations, make sure you know which equation they're actually looking for. This is really common with benzene questions. For example, I might get 2 different questions about the chlorination of benzene or the bromination or whatever I'm substituting onto a benzene ring. So formation of the electrophile for benzene, that's going to be, how do I make the thing with the positive charge? So it's going to involve the catalyst reacting with a molecule of chlorine, pulling off a chloride ion, whoops. So you get that minus. And so electrophile means, how do I make the positive one? If it was nitration, it would be, how do I make the NO2 plus? That's another really common one. But if I just want the overall reaction, then I'm just starting with benzene. I'm actually adding Cl2. So Cl2 is the reagent and AlCl3 is the catalyst because it gets regenerated in the mechanism. And then I'm just substituting. So it would simply be swapping an H and a Cl round for the overall reaction. And I'm not doing anything with the catalyst because it's an overall reaction and catalysts aren't involved in overall reactions. Another common place where you get that, of course, is free radical substitution. You've got all your different steps, check whether they're asking for initiation or propagation, or if they're just asking for an overall substitution reaction. Okay. Oh, we've got 15 minutes to do synthesis and analysis. I think we can do it. So synthesis can be a bit scary. Lots of steps, lots of things to remember, but also trying to apply them for to different, something that we've maybe never seen before. So my recommendations, working backwards. Yesterday, we talked about revision techniques. And one of the things I said with functional groups is don't just learn what that functional group does, learn how to get to that functional group. So I'm starting with benzene, sure, but the main thing is I have an alkene at the end. So I would be thinking, how do I make an alkene? There's actually only a couple of ways to make alkenes. You either have an alcohol and you remove the water, or you have a haloalkane and you remove the bromine. So then I'd be like, okay, well, what can I add to benzene that I could make an alcohol out of? I could add something with a C double bond O. I could reduce it to an alcohol, then I could take the water off. It's easier if you start at the end and try to think about what you could have made, like what different functional groups you could have had there. Extra carbon atoms, look out for that. So sometimes it's nothing about the functional group, it's about the fact that you've added a carbon. So if you start with 2 carbons and you have got 3 and they're joined together carbon to carbon, you've got to do something with cyanide, unless you do Edexcel, in which case it might be a different reaction. So cyanide is a thing to look out for. You're going to probably see some nitrogen somewhere, but generally the clue is an extra carbon. And then another thing to look for is, did the functional group kind of hop? Or did I have like a bromine on one end and then it suddenly became an OH somewhere else? So if you have a functional group hop, like this one on the right-hand side, where I did have bromine on the first carbon and now I have bromine on the second carbon, you can't do that. Like you can't just, there's no sort of swapping reaction where a functional group hops from one reaction to the other. So I must have had to go through a double bond and then add to it in order to get something to move onto a different carbon. So that's a few things to look out for, especially working backwards. And also just take a breath. Okay, so if you get stuff like this, take a breath. Another tip, which is surprisingly effective, you're going to think it isn't, but anytime that you're getting stressed or you're overthinking, like, you know, you can hear loads of stuff going on, count backwards. 5, 4, 3, 2, 1. In your head, obviously, in an exam. Don't do it out loud. It just cuts through it actually sort of cuts through that nattering in your brain and gives your brain a step back, and it re-engages the frontal bits of your brain as opposed to the panicky bits of your brain, because counting backwards involves using that part of your brain. So we want to be logical about this. There's loads of stuff going on. These are 2 separate questions, not the same question. And obviously there are, on the right-hand question, there's lots of separate questions that go with it. So things to avoid the stress. Look and see if there's more than one functional group. So in that left-hand example, there is an alcohol and a carboxylic acid. So you need to be doing that thing we were talking about yesterday with functional groups and going, what do these functional groups do? What are they like? What do alcohols react with? What do carboxylic acids react with? And think of it that way, and also do that backwards step where you're like, okay, how do I get to an alcohol and how do I get to a carboxylic acid? And then rather than looking at the whole molecule and thinking, oh, how do I get to 2-hydroxybutanoic acid from that? Look at individual parts. Because, for example, the OH isn't changing in that first one, and that's because all I'm doing is hydrolysis of the CN bit. The right-hand side, there's loads of stuff going on, but there's also lots of clues. And so you'd want to make sure that you're looking at all of the clues, and again, a little bit of working backwards. So I can look at my final thing, methyl methacrylate, and go, oh, that's got an ester in it. We only know one way to make an ester really is like alcohol and carboxylic acid, especially because it says there's an acid catalyst. So all I've really got to work out is, have I got the acid or have I got the alcohol? Well, it must be the acid because the C double bond O is in like the main bit of the molecule. So those are little ways that we can go through backwards and we can get little parts of it. And sometimes as well, we don't need to know all of it. So don't worry, like, don't start to panic about things they're not even asking you about, because they might not even say anything of interest about particular reaction. They might not want to know much about it at all. Okay, so reaction pathways: keep calm, count backwards, go backwards from the bottom, think about functional groups individually and see what they do. Last, we're just going to look at analysis, because analysis questions, they got a lot of information as well. And we want to be able to be efficient and not waste time. So these are 4 different compounds. You have a whole table of infrared, like different wave numbers, different bonds. Really though, all you really need to know is about 4 different bonds. You need to spot an OH. You need to make sure, there's an OH there as well. You need to make sure that you don't confuse a CH for an OH. And if you look carefully, you can see that the CH is just a little bit below 3000 and the OH is sometimes stretching across it, but always going above 3000. Whereas, and the OH is so much more round and the CH is so much more spiky and messy because there's lots of CH bonds and there's usually only one OH. You also need to be able to spot a CO. And you need to be a little bit careful on that. So a CO has to be around 1700. If it's around 1650 like that one, then it's actually more likely to be a C double bond C. But you should also get some clues about that. So don't forget to also look for clues. Like it might tell you that it reacts with bromine water. It might tell you that it contains a C double bond A. Other than that, there is nothing much else to waste your time with infrared. It is such a tiny piece of information about a molecule because half of that spectrum is unreadable below 1500. And so therefore you really are in looking for like 4 things. Very, very occasionally I may see a C triple bond N or an NH, but they're quite rare. And you've got the thing in your booklet to tell you that. If you're writing about infrared, don't say it's got a CO and an OH, so it must be a carboxylic acid. You need to put other stuff together to decide whether it's a carboxylic acid. You can't always assume. Okay, what about mass spec? How is that useful? Again, make sure you use the stuff they give you in the question. These 2 compounds, you already have the empirical formula. So once you've worked out that it's C3H6O, you are also told that they are carbonyls, so you know they have C double bond O. You check what C3H6O adds up to. The MR is 58. That's the same as both of these mass spectrum. So rather than get really hung up and getting straight into the mass spectrum, don't do that. There's only 2 possible structures with the formula C3H6O that contain a C double bond O. There's actually only propanol and propanone. My other little tip for mass spec, if you get something a bit more complicated than that, which, that's pretty basic, is to draw it out using numbers that represent pieces of the molecule, the masses. What do I mean by that? CH3 adds up to 15. That's a 12. that's a 16. I'm unlikely to actually break that double bond. And that's a 15. Whereas the other one is a 15, a CH2 is a 14, a 12, a 16, and a 1. So that's a useful way of visualizing how the molecule might break up. And straight away, I can see that one of them will have a peak at 29 because I've got 15 plus 14, and the other one won't. So I can see how they'll be different in the mass spec. And I could just look for the one that has a peak at 29, which is the one on the left. So that would be my propanol, and the other one would be my propanone. There's also like a big peak for losing one hydrogen on the one on the left. So draw out your CH3s, CH2s, etc. So you can see how it will break up. And then when it comes to NMR, there's a lot of information we can get from NMR. So it's helpful to prioritize it. My order of importance for sort of like what will tell you the most. We're going to assume that when you have an NMR question, you already know some stuff. And in fact, I already know some stuff about this molecule. So don't ignore what it gives you in the question. The order of importance, I would say, is the number of peaks, because the number of hydrogen environments tells you a lot. It tells you about symmetry. It tells you about whether there's any similar environments that are the same as each other. How many hydrogens there are. So this spectrum, I can see a peak with a peak area of 6. You can't put 6 hydrogens on one carbon. So that immediately tells me there are 2 CH3 groups that are the same as each other, which means they're either attached to the same carbon or they are opposite ends of like a symmetrical structure. Peak area, the other thing I'll do is I'd add it up. 6 plus 3 plus 1, that's 10 hydrogens. And I would check whether that's the actual number or whether there might be 20 hydrogens in my formula. And splitting patterns, that's also really important. By this point, I might have already eliminated some possible isomers just from the number of peaks in the peak area. Splitting patterns is usually the last bit of information I need. Chemical shift tends to be something that students go to look at because you've got it in a data book and you can cross-reference it. But I would say it's the least important bit of information, because by the time you look at the chemical shift, you could have worked out the whole molecule without knowing what the chemical shifts were. So I'll do this one as an example because it's really helpful. Don't forget to use what it tells you. A lot of people think that just because it says it contains these 3 elements, that you couldn't then work out what the formula was. It's like, well, I don't know. It doesn't say what percentage carbon and hydrogen and oxygen are. So how am I supposed to work it out? Okay, well, it tells you it has 2 carbonyl groups. So it has 2 C double bond O's. All right. So it's got 2 O's. It says no other functional groups. So I'm going to take 114. I'm going to minus 32 because that's the mass of 2 O's. That will tell me what my C's and H's add up to, which is 82. You can't join carbons and hydrogens together in absolutely any order that you like or any ratio that you like. There are rules. It's either going to be like CN H2N, or maybe there's like a little bit less hydrogen. You're not going to have like 20 hydrogens to 3 carbons. So I'd basically look at what's the maximum number of carbons I could have. I can't have 7 carbons because that adds up to 84. So I must have 6 carbons. When I work that out, it leaves me with 10 hydrogens. So I actually know it's C6H10O2. So you can work out molecular formula a lot of the time with quite a small amount of information. I can then work out there are 10 hydrogens and there are 10 hydrogens in that spectrum. So those actual peak areas are equal to the actual number of hydrogens. I know that I've got 2 C double bond O's. So 2 of my carbons probably don't have any hydrogen on them. And the other thing that I would look at, so that tells me I have 2 lots of CH3 and they're on the same carbon. and they are split into 2, which means they must be next to 1 hydrogen. So I've already done all of that just from that peak there. I know that this hydrogen is over here because this hydrogen is 1 hydrogen on its own and it's split into 7, which means it's next to 6. I therefore know there's no hydrogens on the next carbon because that hydrogen is only split by those CH3s. And so that must be one of my carbonyls. Finally, I know that that is a CH3 because there's 3 hydrogens there, and it's a singlet, so there are no hydrogens next to that, which means that I must have my 2 carbonyls must be in the middle. Can't have any aldehydes, because if I had an aldehyde, I'd really clearly have like an H that was corresponded to a hydrogen aldehyde, and I don't. Okay, I've done all right for time, but I'm aware that it is sort of just gone 1:45. I'm not going to go into the, actually no I am, I'm just going to very quickly go into the mechanisms bit, but I'm going to ignore that next question. Someone said about if you have an unfamiliar mechanism, bonds going out means I break the bond, so arrows going away means I break the bond, and then arrows going towards means I'm making a new bond. So if I looked at this thing on the left, the first thing I would do is make sure that I've drawn everything that hasn't got an arrow completely unchanged. So nothing happened to this bit. I know that that has stayed the same. So I'm going to draw it exactly the same. I have an arrow coming out of the double bond, so that means the double bond's not there anymore. I have an arrow going from an O towards a carbon, so that O is now bonded. That O there is now bonded. I also know that I broke this bond here, this double bond, and I know that that arrow came out of the double bond and towards the oxygen, which means that one of the carbons must be bonded to it, and it must be that one. So it's just an application of logic in either working at, what was broken and what was made. On the other side, it's actually asking you to draw the arrows a little bit harder, but if I look at the product, it says NH3 plus, whereas it was an NH2. So that means the N must have joined onto an H, made a bond with an H. It's plus, which means that the hydrogen didn't have any electrons with it, which means that that must be going back on there. And the other reason I know that is because that N doesn't have a charge on it in this part here. So the COO minus does, but that was already over here. So that hasn't changed. That's part of the molecule that stayed the same. The NH is now NH, not NH2. And therefore, I have just broken the bond. And excuse my arrow, because I was drawing on a really small screen there. So my arrow should be touching that bond and not kind of overlapping it. Okay, went through a lot of stuff very quickly. If you're not already aware, I do following on, not next week, the week after, doing 2 A-level lessons a week, doing loads more detail on exam questions. And I've got a few spaces left in the live classes. So if you're interested, email me. Or alternatively, you can just access recordings for that as well, which is a bit cheaper. Okay, I will take any questions for a couple of minutes, although I've got another student at 4. But if you have any questions at all, fire them my way. And I apologise for the technical issues. Don't think my computer liked having the pen and the PowerPoint on at the same time. No questions? I'm all right with that. Dumbfounded. More than likely. Okay. Thank you very much. Thank you guys for coming. It's I like to give people a hand with their revision because this is a overwhelming area. And keep an eye on your inbox because I'm going to send that email out with the recordings and also the links to the other documents I talked about yesterday. And other than that, have a really good Easter and crack on with that revision.